Good afternoon. This is Caroline Hazard with the Jump into STEM team, and welcome to our third webinar in the series for Round 1 Challenge, Using the Right Data at the Right Time. All attendees are in listen-only mode. This webinar is being recorded, so we can view that later. It will be posted on the Jump site, jump.ideascale.com. And if you have questions at all during the presentation, feel free to chat those into the window. We will try and answer those if we have time. So let's go ahead and get started. Today we are going to go over a quick overview of what is JUMP and how it works, where to go, giving a quick tour of the website. A lot of this information is already posted there, and you can view the recordings from previous webinars to see how things work. Then we're going to get into a quick overview of the current challenge, connecting the right data at the right time. What are we looking for? And with that, we will lead into our featured panelists. We're really excited to have Dr. Omar Isaac Asensio from Georgia Tech presenting on real-time data analytics and energy conservation, and then also Tom Kobe from Emerson Control Technologies with connected solutions in the future with millennials. Dr. Omar Asensio is the assistant professor and class of the 1969 teaching fellow in the School of Public Policy at Georgia Tech. His research focuses at the intersection of data science and public policy with applications to energy systems and behavior, smart cities, vehicle electrification, and applied machine learning in transportation and mobility. He conducts randomized field experiments and uses statistical and computational methods to model the human and behavioral dimensions of energy use. At Georgia Tech, he is a faculty affiliate with the Institute for Data Engineering and Science, and the Machine Learning Center, the Strategic Energy Institute, and the Climate and Energy Policy Laboratory. So we're really excited to have him on hand here to kind of spur some thoughts for you to think about how to respond to this challenge. And then we also have Tom Kobe, who leads the residential Internet of Things smart home business model search and customer discovery for Emerson's commercial and residential solutions. He is both the entrepreneur and the intrapreneur side of innovation, whether it's overcoming internal stakeholder constraints or working through experimental design and execution. Tom understands the critical milestones and journey of an idea to commercialization. So he'll give you some great ideas to think about as well. So let's just do a quick review of what is JUMP. Our purpose here is to expand our reach to university and college students. We're seeking to cultivate the advancement of women and minorities in the STEM field. And we're doing this by offering an online flexible platform for colleges and universities to engage their students in innovative design and thinking about today's problems in building technologies. And we want to motivate creative thinking among students and ideation for the advancement of buildings research and innovation. So we do that with this online website. You can see the address there, jump.ideascale.com. This is the home page, and this red arrow points right to how it works. That's where you'll find a video that walks through the website and how to get going. It's pretty straightforward. There's always a question box at the bottom if you ever have a question, and we'll try and answer that. If you want to get right into where you see the challenges and what topics are there, you want to click on this area here. Right now we only have one round open. In the future, there will be other buttons here to click for rounds 2 and 3. When you click that button, it's going to open up a window that looks like this one here on the right side of your screen, where you can read about the specific challenge, what we're looking for if you scroll down further on. You'll also find the recorded webinars here from the previous webinars we've had. There'll be a similar type of page for any future topics, challenges that are going to open up. So then when you're ready to submit your idea, after you've reviewed the challenge and the eligibility criteria and thinking about what you need to do and what you want to submit, you can click this Submit a New Idea button, and you'll see a form that will fill out like this, where you provide your title, you have a brief text field to summarize your idea. In this area right here, you can upload a PDF or other data files with graphics or data and that kind of thing. And if you like, tag your idea so that others can review your idea and comment and vote, and we can learn from each other in this crowdsourcing effort to advance building technology innovation. So we have an updated schedule. The current challenge is being extended to be open until November 30th. We also have the exciting news that rounds 2 and 3 challenge topics will be coming soon in October, which essentially is next week. So look for information on that. The topics are designing new methods for fault detection in buildings and pushing the envelope with wall retrofit designs. So those are coming soon. Now let's get to this current challenge and what are we looking for. So this challenge is connecting the right data at the right time to improve residential building performance. We're looking to understand how can we tackle connecting behavioral motivations with increasingly accessible energy use data. The objective of this challenge is to identify and design approaches to influence homeowner decisions and optimize their energy use. So we want your ideas on that. We're looking for things like how to effectively baseline the homes or a specific end-use appliance's energy use. Or perhaps your idea might think about experimental models to test, monitor, and influence energy use behaviors. We're also looking at how can we better visualize, make data simply presented and the data schema to capture and display that information so that it motivates actions. These are the real challenges that we're faced with in the market today. And so we think that students across the nation can help us think about that. So we're looking for your ideas. With that, I'm going to transition it over to Dr. Asensio for his presentation. Omar, are you there?
I'm here.
Great. Let me shift over to your slides and you let me know when you're ready. Sorry about that. Here we go.
Great. So it's a pleasure to be here with you here today. I'm going to try to give a little bit of a sort of inspiration as you think about your challenge and maybe motivate some ways that we can think about using real-time data analytics in ways that can impact energy conservation behaviors. And in this presentation, I'll focus on the household residential sector. So next slide, please. Okay, so the main behavioral challenge that we have when thinking about energy use in buildings is that we often don't really understand what the sources of energy use are in buildings. And we say that, of course, electricity is often invisible. That is, we don't really see how our individual usage at the appliance level or maybe more generally have an impact on the overall consumption. And so oftentimes when we get a bill at the end of the month, every 30 days, maybe 60 days, unless you're really checking frequently, it's often too late to make any behavioral changes once you get the bill. And so there's a large literature looking at information feedback as a way to connect the right data at the right time, and that is, how is it that we can provide the right information about energy consumption to individuals that will give them an opportunity to perhaps make changes like turning off the lights or adjusting thermostats, or probably more effectively, unplugging phantom loads and any kind of consumer devices that may be plugged into the wall. So what we say is that households often have this sort of imperfect information about what are the effective conservation behaviors. And secondly, we might also be kind of inattentive to energy costs, given this gap between the consumption decision and then the feedback. Next slide, please. So we have this kind of information revolutions already here. We have a whole, a number of different smart meters and gadgets and all sort of technologies that allow us to look at consumption, not just every 30 or 60 days when somebody from the utility might come out and do a meter reading, but also give us the ability to perhaps at the individual level, look at our consumption in real time. And so while we have a very good understanding of perhaps using a number of these internet connected devices to provide information feedback, we don't really have a very good understanding about how we should be communicating energy use information in ways that can really motivate individuals to take actions to conserve energy. Next slide, please. And so a main research question we could ask is, using these new smart metering and information technologies, which provide a wealth of new sources of data, how can we motivate individuals to conserve energy? Next slide. And so there's quite an extensive literature now looking at behavior change in the residential energy sector, and of course the home energy reports, which many of the utilities have been upgrading on a national basis with social comparisons and social norms, have been taken off and been quite successful and showing short run and long run behavioral changes by using behavioral science-based approaches, like, for example, comparing one to one's neighbor. And so benchmarking and social comparisons has been shown to be one effective approach to non-price-based behavioral changes. There's also another literature that is focused on using third-party certification schemes. So this is like efficiency signaling in, say, commercial buildings, where we might look at the impact of, say, Energy Star certification or LEED certification, or perhaps voluntary participation in a Better Buildings Challenge as a way to kind of motivate and inspire managers and building occupants in commercial spaces to invest and signal to the market that the building is more efficient. And so these kinds of both price-based and non-price-based strategies have the effect of addressing investment inefficiencies, that is lowering search and information costs about what to do. Second, it's about reducing energy use externalities, and that is addressing the emission reductions through conservation actions. But also, more importantly, within the world of smart meters and real-time data, it's about the consumer acceptance of new technologies, and the human and social factors turns out to be quite an important component of being able to achieve large-scale energy use reductions through changes in behavior. Next slide. So this slide shows a meta-analysis of the energy conservation literature field experiments dating back to 1975. So we have 37 years of published field evidence that has looked at a number of different both monetary and non-monetary approaches to energy conservation. And on this slide, what you see is if you're sort of above the horizontal line, that's kind of suggesting energy increases relative to a control group. And if you're below the line, that's looking at conservation actions versus a control group. So one of the things I wanted to point out is if you look at the first two bars, it turns out that just providing feedback alone or energy saving tips, like you might say get in your standard utility bill, it turns out that if you just look at the published evidence and the field experiments, what we see is that in the literature, feedback alone is often insufficient to drive lasting behavioral changes. And so it turns out that the real-time feedback and the home audits and consulting seem to be some of the most effective interventions. Of course, social comparisons have been shown at large scale to have long-run effects, but of course we can see that if we unpack kind of this treatment effects from social comparisons, we often have that certain communities may be more responsive to neighbor comparisons than others. And then one curious finding is that just providing information about saving money, at least from the published experimental evidence, suggests that there's not a significant amount of conservation just by providing, information about saving money. And so given this, we're going to try to test some alternative approaches to combine sort of information-based metering and feedback with different ways to frame information to sort of reframe the conservation decision. Next slide, please. So I'm going to talk about a field experiment that we conducted in Los Angeles in multifamily residential households. So here is a look at the website that we put together. And what we had is a sort of real-time appliance level metering kit that provided households in the study with a detailed breakdown of their appliance level consumption. And so oftentimes, even with the installation of smart meters in your local utilities, you may only have real-time information, or at least every 15 minutes of an update as to what your consumption might be, but you don't really have a detailed breakdown of how that is distributed across your appliances. And so oftentimes, while consumers can get a signal that maybe in 1 month or another they're over-consuming versus some kind of goal or maybe a benchmark neighbor, we really have no visibility into how that breaks down at the appliance level. So here we provided real-time appliance level feedback. And so you can see in the pie chart, it kind of splits it up into the refrigerator, the lights, the heating and cooling loads, for example, the refrigerator, the dishwasher, other kitchen appliances, and of course, the largest piece of that pie, which we don't often think about when we think about conservation, is actually the electrical plug load. So based on this particular user's profile, the most effective conservation action is not necessarily to turn the lights off after you've not used it, but it actually may be to focus on phantom loads and the electrical plug load. That is anything you plug into the wall, like computers, charging a cell phone, and other consumer electronics. Next slide. So we tried to provide some additional information along with the metering the appliance level feedback. And so we randomly assigned households into one of two treatment groups. The first treatment group received a classical economic story about saving money. So if you save energy versus your efficient neighbor, you can save X amount of money. And the other message focused on the non-monetary social costs of energy consumption, and namely that is through air pollution impacts through energy system. And so we randomly assigned households to receive either a health-based message related to the known impacts for from energy consumption, and the other set of households received a classical message about saving money. Next slide. So here's kind of another look at the feedback. So users really had a chance to log in and look at their consumption sort of in real time. And there was a now button that sort of had a real-time signal of their consumption, so they could plug in, like say for example, a hair dryer, and they could see as the signal kind of kilowatt hours goes up, sort of in real time and experiment. So part of that was providing users with a way to learn and to test what are the most effective conservation actions. And so in the bar at the top, we see that's basically the treatment message. So you either see a message about cost savings, or you would see a regularly updating message about health. And in the middle is the quite familiar sort of structure that we see in many home energy reports throughout the country, and that is you might get sort of a bar that shows your current consumption for the current period versus, let's say, some kind of benchmark, and that is kind of in this case it was the efficient neighbor, but the reference point can be an average neighbor, for example. So this would give us a way to sort of invoke this sort of social norm, and that is how are you consuming versus your efficient neighbor. Next slide, please. So it took us a little while to get the wording right, and so we had to make sure that the wording was scientifically verifiable. So we took the individual apartment's consumption in kilowatt hours and used the Environmental Protection Agency's EPA's greenhouse gas equivalencies calculator to look at some of the social impacts of energy consumption. And so what we do here is convert kilowatt hours into, say, pounds of air pollutant emissions. And we didn't really quantify the health impacts, but we just give a listing of known health impacts, such as, in this case, childhood asthma and cancer. So what we did in one framing of the conservation decision is, this is all about self-interest and I'm saving money and it's going to benefit me. Whereas the health-based message, which is a non-monetary message, focused on the social impacts, which both have a benefit to myself, from having reducing non-base load emissions, but also benefiting my community as well. So these were the two different framing interventions. Next slide, please. Here's just a quick look at the metering kit that we deployed, and so there's a reference to the paper that's been published by my colleagues, and it basically just showed a simple way of using kind of off-the-shelf tools to build an energy gateway that would update in real time. So in this case, we were collecting data at 1/30 hertz for every single appliance in the household. So you can see that the sub-metering provided new capabilities that weren't previously available, and at the same time provide a wealth of data what then can be used for real-time analysis and computation. Next slide, please. So here's a look at the actual field site, and I just wanted to point out that, of course, we had to recruit subjects to participate in the study, and so we randomly assigned households in these two block groups into one of the two treatments, and then of course we had a dedicated control group that didn't receive any information messaging, but we still had the real-time appliance level capabilities that we would see on the back end. So that served as our counterfactual reference group. Next slide. So this is just a quick slide to show that we tested and verified that, of course, in 12 months prior to the beginning of the study, and then during the 6-month baseline period of study, that we didn't find any significant differences in observable characteristics between households. And this is just a quick check in any kind of randomized trial, is an important check on the effectiveness of your randomization procedure. Thank you very much. Next slide. So I'm just gonna quickly highlight that we did conduct a survey to get household characteristics. So we do control for household characteristics. And importantly, because we monitor or meter energy consumption at such high frequency every 30 seconds, that we had to include more rigorous weather controls. So in this case, we aggregated at the hourly level using the nearby weather monitoring station and including the heating and cooling degree hours as a check and a control on the energy consumption. Next slide, please. So here's a look at the daily load profile for this particular community. You see that there seems to be a local peak around 9 a.m. when people are presumably getting up in the morning and getting ready for their day. And then there seems to be a little bit of drop off. And then of course, the peak consumption for this particular community occurs in the evening around 9 p.m. So the data really allowed us to look at usage signatures at a very detailed high frequency rate, so we can learn a lot about the daily consumption patterns. Next slide. And because we had such the capability to meter at the appliance level, here we show that, of course, the appliance signatures are really unique to each individual appliances. So there is an interest in developing algorithms that can automatically detect appliances and be able to understand how you could possibly do what's called load shifting, and that is target interventions in ways that you can sort of nudge consumption between from periods of peak demand or peak use to non-peak periods. So that's a big area of interest for ideation. Next slide. One of the big things is that we often do these behavioral interventions, and we hope that sort of the message or the intervention that we provide, that users actually see the data. And so one of the big opportunities is to use some kind of real-time analytics tracking, either through the mobile devices or through websites, to be able to track whether or not people actually see the information. And so what I'm showing here is a time series of Google Analytics page views for the active users in the community. And what we see is that those that were randomly assigned to health messages, for some reason, seem to be more engaged than those who receive these monetary messages. And so the spikes that you see every approximately 7 days in that chart is the time that we would send the weekly email reminders. So engaging with individual households is a lot about how to communicate and what is the right frequency of communication to really engage households at the right time. Next slide. So here I'm just going to show the overall effects. So for the cost savings group, and consistent with our 37 years of published meta review, we don't find any significant conservation effect at the end of the experiment for households that received the cost savings messages. On the other hand, the households that receive this health-based message reduced energy consumption versus the control group of approximately 8%, which is a fairly large number in the sort of social normative literature. And households with children saved up to 19%, which were highly motivated based on the messaging. So this was quite an interesting finding that in retrospect, it kind of makes sense that households with children would be most motivated, but at the time, it was sort of the first demonstration of the use of health-based messaging, environmental health messages, as a non-monetary strategy to motivate conservation. Next slide. So here I'm just going to show you a little bit of the computational dynamics, and because we can estimate treatment effects in real time, what I'm showing here is the black line is representing the cost savings messages. And so if you're below the line, of course, that's energy savings, and if you're above the line, that's energy increases versus control. What we find is that initially with these new metering technologies, households get very excited, and so there is, even with cost savings messages, initial conservation. It's just that by the end of 90 days, the cost savings messages don't have a very lasting effect, and so at the end of the experiment, we don't have any significant conservation effect after 90 days. Next slide. So now in the blue curve, here we show the health messaging group. And so we find is, consistent with the cost savings group, both of these groups seem to really like the idea of being able to meter their appliance consumption in real time. And so there seems to be this sort of learning curve where initially there's conservation. It's just that if you frame the conservation decision based on health, it seemed to be a more lasting intervention. And so by the end of the randomized controlled trial, net of our household characteristics, net of weather controls, and net of any seasonality controls, we find that the health-based messages seem to have a more lasting effect than the simple cost savings and monetary strategies. Next slide. So in summary, we see that we can sort of affect the way consumers and the way households interact with energy conservation decisions simply by changing the nature of how we frame the conservation decision. So if you look at this 8% conservation effect and use the published price elasticities from California, that's equivalent to a 20% price increase using a long run elasticities. And if we use the 60-day short run elasticities, that is equivalent to a price increase between 30 and 60%. So quite a large impact simply by changing the nature of how we frame energy conservation decisions and using the technology to do this technology-assisted behavioral changes. Next slide. So let me just close off this talk now with some ideas and suggestions for our challenge participants. Next slide. So here I'm just put a quick listing based on some of these commercially available now energy gateways that can be bought sort of over the counter and enable and activate these sort of appliance level end uses. So one of the big challenges now that we try to make energy use, which is typically invisible, and try to activate that, we have a number of different commercially available devices, and maybe we'll hear more about this later in the seminar, that can help us activate some of this data. And so once we start collecting data, then the question is, what can you do to analyze it? So next slide. So there's some considerations about how you frame the information, how you build a user interface to basically have people quickly understand it, maybe get it in real time. And so here we're showing you one particular approach that uses various algorithms to sort of learn about what are the underlying uses. So for example, here an iron was on for 8 minutes, or the dryer was on, dryer was turned off, for example. So it provides users with this real-time information. Consistent with the previous research, it's probably a good idea not just to provide users with the raw feedback about their consumption, but as we saw in the previous randomized trial, it may also be a good idea to think about new ways to communicate that conservation decision in ways that can motivate people and use behavioral science-based interventions. Next slide. So once we start collecting this massive data, now we have this problem that because the data is coming sort of in real time, and in the language of big data, we call it big velocity data. And so here I'm just using one kind of simple tool that's available to the public, and that is using the Microsoft Azure cloud-based services, and a number of different companies have various services that are similar, and that is here we have the ability to do real-time stream analytics. So once you've be able to use an application programming interface to connect your IoT devices and gateways, tools such as these enable you to build in real-time dashboards and also to provide analytics on the back end in order to analyze some of the data. Next slide. And so in closing, just wanted to leave off with one closing idea, and that is, it's one thing to design an app and allow people to look at energy consumption, but we can also think about new ways to engage with energy usage information. And here I'm showing you one concept that uses AR or augmented reality type technologies to activate energy use information in ways that now we can compare at different scales of analysis. So we can go down to the individual appliance level, to then maybe to the individual unit level or apartment level, to maybe at the building level. And here would be a concept that would allow us, at least a campus manager or a building manager, to look at consumption in real time across multiple buildings or say small community. So this would be an example of community scale building feedback and visualization. And with that, I think I will hand it over back to you, and thank you very much for listening.
Great, thanks so much, Omar. That is really, really fascinating research that you've done here. Let's go ahead and I'll remind folks and let you know you can type in any questions you might have for Omar or me, and then also Tom. Get you back to the beginning here, Tom. So up next, we've got Tom Kobe from Emerson. Are you there, Tom?
I am. Hello.
Great. Why don't you go ahead?
All right. Well, thank you, Carolyn, and clearly awesome work being done by Dr. Asensio and his team. When you talk about behavior change around energy consumption in the home, one of the largest energy consuming appliances in the home are the heating and air conditioning systems. And when you talk about HVAC for short, there is almost always a service provider involved, an HVAC contractor involved. And so when you talk about behavior change for the homeowner, it also includes behavior change for the technician and the owner of that HVAC business. So we're going to take a little bit of a different angle and look through the lens of commercialization and monetization for the rest of the value chain aside from just the homeowner. So it could be the manufacturer, the distributor, the HVAC company, and the HVAC technician. So with that, next slide, please, and we'll go ahead and hop in. All right. So we'll talk about the smart home and the reality of where it is today and where it's going. We'll talk about monitoring and FDD, or fault detection and diagnostics. And then we will talk about those paradigm shifts required to change the behavior for the HVAC company, for the technician, and for the homeowner. Next slide, please. So it's legit, finally. The smart home is here. There has been many false starts, but it is finally here and taking hold in the States more than anywhere else. You can see here from the chart over on the left, the U.S. Is not only leading the way, but leading the way in acceleration as well. Next chart, please. So that's critical. Anytime you want to be disruptive is to get, kind of that tipping scale or that mass market adoption. And when we look at the smart home, we look at it in kind of three slices. The first slice over on the left being what we call infotainment. The penetration in this slice is very high. Most of you have probably used Pandora today, or Netflix, or any of their streaming services to stream media, be it video, audio, or the appliance that streams those services. Then we've got the second slice, which is security and access. I like to talk about that as using your phone as a remote control. So, you could go and, turn your light off at the light switch, but you're going to use your fancy little app and control the light switch from your phone. Some of that stuff's novelty. Some of that stuff is really a high value, especially when you get into the security side of things. So the cameras, locks, garage doors, those sorts of things. This is the fastest growing slice of smart home, and some brands that you all are familiar with there in the middle. And then the last slice, which I'm super passionate about, is this slice that's really the infrastructure of the home. It's the mechanical and electrical systems of the home that make it live and breathe and make it habitable. And this is the newest slice, or the slice that has the biggest opportunity for disruption and growth, which is where me and my team spend most of our time, but it is the air, water, and energy systems in the home. And when you look at those two slices over on the left, it's really about compatibility, good APIs, working with all the smart home ecosystems. Where the slice on the right is a little bit different because it requires deep domain expertise, and it requires tools such as stream analytics tools. In my business unit that I work with, we use Amazon Kinesis, which is similar to the product from Azure. So you need deep domain expertise, and you need a lot of kind of cloud computing horsepower to be able to get the value out of that slice of smart home. And then the glue that really holds all that together is those ecosystems for integration. So those brands you're probably familiar with are the Apple HomeKits, the Google Homes, Amazon Alexa, Samsung SmartThings, If This Then That, Wink, and many more are coming onto the market, and they are really the primary drivers in why the smart home is real today. It allows a design your own smart home, bring your different devices, and then have that interface, be it voice or a unified app that connects all those products together so that you have a seamless interface to have all those products play well together. I will give you a hint on this slide for something that is very important to me and in this space right now. Voice has now become critical in that ecosystem layer. If you look at Amazon Alexa, it is now the fastest growing single SKU from a company to ever hit the market. It's accelerating faster than when the iPhone hit the market. So hint, hint, voice is super critical in how you change behavior for the technician and how you change behavior for the homeowner. And there's some really cool tools out there for voice. Next slide, please. So now we're going to shift over into specifically talking about HVAC. So we'll talk about monitoring and fault detection and diagnostics. Next slide, please. So the key to what's happening in our space, both in what Omar was talking about when you talk about like energy disaggregation at a whole home level, or looking at appliance level consumption and diagnostics, is low-cost sensors. Low-cost sensors are unlocking new affordable product categories and new revenue models by being able to take low-cost, off-the-shelf, mass-produced sensors and kind of designing your own IoT solution that you then pipe that data to the cloud through those analytics platforms where you can analyze those streams and put that big horsepower on it and get some good data to come out the other side. Most times you're communicating over Wi-Fi. Some cellular has gained traction, but Wi-Fi to a broadband provider is still the primary way to get data out of the home, although cellular is starting to take hold. Next slide, please. So when you look at how HVAC FDD has been done in the past, it's typically been done at the control level, which is the thermostat. And the best smart thermostats in the world, Nest, Ecobee, Sensi, and there's many others, have very limited sensor sets on their hardware. So you can look at runtime compared to set point, meaning how long is it running compared to the point that the thermostat is set at. You can look at temp limits, high or low, humidity limits, high or low, and some of the better ones are able to spot some inconsistencies in the ignition cycle of a furnace. The only way to get a holistic view of the health of the system and be able to accurately detect those faults and do high resolution diagnostics is just to have more sensors. So our data shows that you're going to need somewhere between 8 and 12 incremental sensors in addition to what is at the thermostat, which is typically 2 sensors. You're typically going to have a relative humidity and a temperature sensor, which gives you what is called indoor wet bulb. By getting those other sensors, it's able to expand your visibility into seeing airflow, the performance of the refrigerant loop, and how those appliances are consuming energy. And when you do that at a very high sample rate, you can glean some really interesting things into the failure of motors or components in those individual appliances. So the key there is more sensors are required to do the level of fault detection and diagnostics needed to really influence behavior of the technician, which ultimately will influence the behavior of the homeowner, because the technician is typically looked at as the expert, and that is considered a tool for that expert. Next slide, please. So the short of it, you've probably been able to pick up on this as I've gone along, but you've got smart sensors that stream data. That data all goes up to the cloud, and when you've got a good analysis engine and good algorithms, we have found that 80% of failures are detected before they occur. So then the hard part is step 3, is how do you get the right information at the right time? Consumers are typically used to driving their air conditioner until it runs out of oil, kind of making a car analogy there. They use the appliance until it completely breaks down. So this is one of the big paradigm shifts for the homeowner, is how do you provide them not just insight, but actionable insight that gets them to change behavior so that they proactively remedy the system versus waiting for it, a consequential failure of a more significant component, which also ends up using a lot more energy. So I spent a lot of my time focusing on how do you get that data right, and some of the slides that Dr. Asensio was sharing earlier with some of those charts around the social impact of their actions, I think was really powerful. And I know that that's an insight I was able to glean, and I will take back to my team. Super insightful stuff there. Next slide, please. Another hint on that last slide for voice. How do you provide actionable insight with voice to get a homeowner to change their behavior? So when you look at the typical monitoring feedback loop, kind of a Deming loop, so typically the sensors are going in on a new equipment going in, a tune-up, or what's called a maintenance visit, or a repair is being made. When those sensors go in, we validate in the cloud, get a good baseline, system's all clear, and then we are looking for something to go out of bounds. It could be a single sensor input, it could be a series of sensors trending over time. That then goes through an analysis engine to validate it, and then that alert goes out. All consumers are different. Some consumers still take their 20-year-old Cadillac to the Cadillac dealership to get a $100 oil change right when the oil light comes on, and other homeowners put a piece of duct tape or a family photo over their check engine light to make it go away. Regardless, it doesn't go away. So whether you change your behavior or do something about it when that insight is given to you, or you wait until there is progression and there's a higher severity, at some point a remedy needs to be made to that failure mode, and then your loop closes round and you come back full circle. Next slide, please. So building this new mental model for the homeowner is super critical. And this is where we are looking at how do we take visual interfaces and make them more approachable. Could it be audio interfaces? Another hint. So we are looking at, teaching this new mental model of not going straight from yellow to red, which is how the homeowner behaves today. I go from a comfortable home to an uncomfortable home. When it's uncomfortable, I call my contractor and he comes over and takes care of me, or he or she comes over and takes care of me. It's all about the yellows and oranges, and how do you message those yellows and oranges to get customers to change their behavior at yellow at best, and at worst, change it at orange. And we never want to see them wait until they change to red, which means you have a critical failure. Next slide, please. Well, you guys have probably picked up on this by now, so let's go next slide, please. So when you look at kind of the life cycle of a customer as it relates to their HVAC equipment, up at the top, you get your brand new piece of equipment. Everything looks great. I want my install to be verified. That's done in different ways. That should reduce callbacks on that brand new equipment coming in. I want to have regular engagement with my system, be it through the thermostat or the controls or some other interface that gives me feedback. One of the primary actions I need to take is listen when my system is not breathing properly and I need to change the filters. Hint, hint. Filters is another area that there's a big opportunity for disruption, and we're starting to see that. And then that last piece that we're working on is how can you empower that predictive repair and maintenance. You move to, call it 5, 6, 7 years down the road. Now you're looking at minor repair and maintenance mode, typically capacitors and contactors and minor lower quality components start to fail. You want to get a hold of those quickly and get those repaired quickly and make sure they're repaired properly so that you delay your time from transition in that stage to major repair replace decision, because that's where things get quite costly. And when you close that loop back around, that's when they start thinking about, do I replace the compressor? Do I repair the system? Do I continue to kind of nurture my system along, or do I go back to replace? And then my loop closes back around again. That is the typical life cycle of a customer that has an HVAC system. We can spend a lot more time on that slide, but trying to be focused on time. Next slide, please. So why do we want a mental model that looks like what we just talked about? Because what I just painted was a rosy picture of what it should look like. And for many of you on the call, I'm assuming ages ranging from, 17 to 30 years old. You may or may not have owned a home or an HVAC system before. So what I just painted was the ideal state. And this is really what current state looks like. Homeowners are completely in the dark about this magic box that sits in their basement or sits in their attic that magically makes hot or cold air come out of it. So because of that, they are left feeling out of control when they do experience a breakdown and the homeowner has to call a technician to come in the home. So even worse is when it happens right when you put it in. A scary fact, 40 to 50% of new equipment that goes in is not installed properly. We'll talk about that here in just a second. When they're sold that HVAC equipment, it's bundled with a maintenance agreement. The contractor does that because they tell them to keep your warranty, you need a maintenance agreement, and it's going to help you keep that running efficiently and effectively. We did a study 3-4 years ago in California, and we looked at thousands of systems that were under a maintenance agreement. Less than 10% of those systems were being maintained to the equipment manufacturer's standards. So then my system broke down. Why did it break down? Because you didn't have good maintenance. So now you have to have somebody come out and have a repair done. Then you start noticing your energy bills start going up. Is it, do I need a new system, or is it because it hasn't been repaired properly? Again, the homeowner is completely in the dark there. And then you're back to that decision again of, do I keep nursing the system along, or do I replace it? So Sad faces are bad. We want happy faces. So next slide, please. So if you look at the Energy Star and the Air Conditioning Contractors of America data on new HVAC systems, depending on the study you look at, 40 to 50% of brand new systems that are just getting installed today are not being installed properly. Not the proper amount of refrigerant put in, not the right airflow set, and many other things, and I'll hit on a couple of them here in just a second. But there is a serious problem when it comes to QI or quality install, and there are a lot of companies that are tackling this space. If you go to the next slide, we hit on a couple of those key areas that these solutions are focusing on. Getting the refrigerant charge right, getting the airflow set right, getting the wiring right, and then having good workmanship when you put it in. There's a lot of detail required when it comes to fitting the system up to the home. So our data that we see from our sensor sets out in the field that are available commercially matches up with the data that we see coming out of the EPA and ACA. So it's neat to see that real world. No, thank you though. I'm sorry. All right, sorry, I'm in a hotel and housekeeping just stopped by. No, thank you. Nice little intermission there. Sorry about that. So yeah, cool to see that live sensor sets coming, or data sets coming from the field are matching up with what we're seeing coming out of the lab. So we feel like we've got good empirical data. Next slide, please. So again, we talked about, we want a happy face. We want a happy customer. A happy customer is provided with actionable insight and feels that they're on a level playing field with the homeowner. I think you guys can get the point. You can read the bullet points around the chart. And if you want to look at this later, you can. Next slide, please. So I want to switch gears and talk about the technician. The technician is critical in the value chain because they are the ones that are conveying the message to the homeowner as to why they should have intelligent HVAC systems, either new intelligent HVAC systems or intelligent HVAC systems via retrofit sensors that turn old existing HVAC systems into smarter systems. So now we have a new mental model for the technician. And a lot of the big hurdles we have to get over with them is just change management, getting them to understand that the sensors that you're putting on the system are the same exact sensors that you carry in your truck every day. They just look a little bit different. And rather than use the interface on a fixed segment black and white LCD screen, you can now leverage your favorite smart device and have all of that data aggregated in a single interface, which provides you much more insight. It's the difference between taking a snapshot at multiple points in time and trying to stitch those pictures together versus watching a movie and being able to see a lot more of the context of what's going on holistically with that system. Next slide, please. So what you can see by turning an existing system into a smart system or smart systems from the factory, which are unfortunately less than 5% of the market right now, and we're not seeing a big uptick there, is you can basically see every aspect of how this system is performing at a very low cost solution. When we say low cost solution, we're talking about like $150 to $250, depending on the sensor set, gives you full visibility into the performance of a system, which is the equivalent of going back and like buying like a 1975 Pinto, and all of a sudden now it can have a check engine light and have all the sensors of the latest and greatest cars. If you want more information about that and you're an HVAC nerd like I am, feel free to reach out to me and I can talk more detail about that. Next slide, please. So when you look at kind of this value matrix, there's kind of three aspects we look at from two perspectives. We look at quality install, maintenance or predicting of problems, and then overall efficiency of the system. We look through the lens of the consumer and we look through the lens of the technician or the contractor. With today's model, it is very difficult to validate the quality of an installation. The best I have seen a contractor do is they send a person that's kind of the expert around to every install they put in, and they manually have to go around and check those systems. California is making an attempt with their HERS Title 24 regulations. Other states are doing HERS as well. It is just ineffective. There are not enough HERS raters, number one, and the competence of those HERS raters is not where it needs to be, often not even as skilled as an HVAC contractor. So really you kind of had the blind leading the blind. I hope I don't have any HERS raters on the call. If so, I apologize. Then you've got the aspect of predicting problems. Right now, there is no warning. Homeowners literally drive their HVAC system until it runs out of oil and things breaks down. And then there's a reactive business model called the contractor. The contractor then has to get a technician out to the home. And when it's the dead of summer, like it is here in Palm Springs, even though it's fall, it's like 109 degrees. That is very tough to manage a business when you've got all these reactive inbound phone calls from customers saying, I need help. It wreaks havoc on the efficiency of the business. And then last is there's no way to detect remotely the efficiency of your system. The best I have seen is what Dr. Asensio talked about earlier, is giving folks some sort of a comparison, be it year-over-year comparison to their current system's performance, or comparison to a neighbor or someone else in the area. Unfortunately, that does not take into account home envelope, which is the how well the home keeps air in the home, or what are called cooling or heating degree days, which is the changes in temperature over the course of a year. And it's very difficult to compare year over year. So from the consumer's perspective, they have peace of mind because they know their system was installed correctly, because they have empirical data with reporting showing that it was installed properly. They are able to know their system is having an issue before there's a loss of comfort or costly parts are damaged, those consequential damages as a result of not taking action earlier. And they know they're saving money and prolonging the life of their system because you can show them, because you're measuring kWs, you're measuring, actually you're usually inferring therms on the gas side. You're able to give the homeowner really good insight into how much energy and money that specific device is consuming. And I might steal some of Dr. Asensio's insights there and maybe add some social impact in there as well, which we are not doing. I think would be super impactful. And lastly, from the contractor's perspective, by validating the quality of the installation before the technician leaves, you have a happier customer. You're able to do the install faster. You're able to eliminate callbacks, and you're able to eliminate having a person follow behind on all the installs to verify the quality of the install. The second point there under predicting problems, that blue square, is probably the biggest impact for the service provider. The operational efficiencies that come out of a data-driven, proactive service model are unbelievable. You can guarantee yourself you have the lowest cost of repair compared to your competitors, because you eliminate most of your diagnostic time and you eliminate callbacks, which are both very costly to the efficiency of the business. And then lastly, some contractors care about this, other ones don't. We like to focus on the ones that do, is you just know you're doing the right thing and you're running an ethical business, doing the right thing for your customers. Okay, next slide, please. So I'm going to hit on this really quick. By having this data, you're able to do some demand shaping. So when you talk about that reactive business model, up in the top left, a reactive business model will look like this in the summer versus the spring. They have unused resources in the spring because reactive customers aren't calling in to ask for help. And then in the summer, you get a massive influx of customers calling in to ask for help because those systems are being stressed, which means you hit your capacity for your resources and you lose revenue. By shifting that demand with sensor data and giving homeowners actionable insight the first couple times their system runs when it's not as hot outside, those customers then proactively fix those systems earlier in the season. It could be giving them a discount for repairing it earlier, or they're just responsible homeowners that realize that they want to take care of the most expensive appliance in their home. That shift in load to the spring allows them to increase their overall capacity throughout the year, which has a huge impact to the bottom line of that business, or in other words, the net profit of that business using the existing resources they already have just by demand shaping. That's over the course of multiple seasons. If you look at the course of a day, the curve that you see in red is typical inbound call volume for an HVAC company. Typically, there's a blip in the beginning of the day when people wake up, realize something's wrong. Then there's the lull in the middle of the day and the big inbound reactive calls coming in from 5 p.m. to 8 p.m. when folks are coming home from school and work. If you look at the bars in blue, that is what our data shows as our contractors that we work with. That is what their workload looks like by using proactive measures and smoothing out that lump that comes at the end of the day. Next slide, please. And we'll skip through this one. That one takes a little while to clear. I know I'm tight on time. So this is what the experience looks like for a customer, and this is what customers want. Without data, you get a reactive phone call at 5:30. You get there, you get there at 5:30. That's even if you could do that. Usually the contractor can't get to you until later in the evening. You could diagnose the problem by 6:02, repair it by 6:34, clean up and leave at 6:45. You have 75 minutes on site, and you have a hot house for dinner. Kids are still doing homework, and the house is probably not going to be comfortable by the time it's ready to go to bed. Versus diagnosing a problem at 1 o'clock, getting there, meeting the homeowner at the home at 3, or if it's identified as a failure mode at the outdoor equipment, the homeowner doesn't even need to be there. You go, you make the repair, it's done by 3:30. The verification comes on that repair. You're on site for 43 minutes. You can run an additional 2 to 3 calls per day, and you have a happy customer because the home is cool by the time it comes dinner time or time to go to bed. Next slide, please. All right, I think I'm at time, so do you want me to stop there, or do you want me to keep going, Caroline?
Oh, no, we should probably wrap it up, but you did give some really great food for thought here. I really appreciate that, Tom. I think if folks can really think about that shifting paradigm and how they might use metadata to influence that shift, I'm sure there are lots of ideas out there. There's lots of opportunity with working with different actors along the value chain. So great stuff there. So we'll close here. If you have any questions, feel free to go to the website, jump.ideascale.com, and type them in. We will be posting this recording online there. And again, thank you so much, Dr. Asensio and Tom, for your time and valuable information. And I hope you have a great day.
Thank you.